Hi, I'm here to talk about how we might build an architecture that has interesting structure in it to help make robot learning more efficient. And in particular, I'm going to focus on compositional, continual, and cooperative learning. So, my overall goal is to make robots that can be generally intelligent. They can do a wide variety of tasks in a wide variety of environments. They could make tea in any kitchen, they could do any kind of household job. So, to think about this and to think about how learning can play a role, we have to figure out the places where learning can help. The way I want to think about the problem is that our job, if we're making robots, is to figure out what software program goes in the robot's head. And what goes in the robot's head is some kind of policy that maps a sequence of observations and actions into the next action that the robot should take. And for our robots, whatever world they go out into, whether they learn or not, we have to figure out what the software is that's going to be there. The way we can think about that is to think about the distribution over situations that our robots might encounter. So they're going to go into some world, maybe a different person's house. They're going to have some job that they need to do. They're going to have a horizon. And the question is, in expectation over all these places, how can we design a policy that performs well? So that's our job as robot engineers, is to find this policy pie that goes in the robot's head and performs well in expectation over the set of environments. So I like this formulation because it really says that if you could specify a distribution over what the robot's supposed to do, there is an optimal policy. But what's difficult about it is that it's hard to find that policy. And all the work that we go into as robot engineers is, I think, in trying to find these policies. So some combination of hand engineering and learning is how we can come up with these things. So first I'm going to think about this distribution over possible domains, right? So some problems we think of are very narrow. The robot has quite a specific thing to do. Maybe, in fact, it just needs to weld a particular thing on an assembly line. Or we might imagine a robot that's very general purpose. So there's a variability in the generality of the tasks that the robot has to perform. And there's also an interesting dimension of variability on how much we, the engineers, know about the domain that the robot will have to deal with when it's put out into the world. And so there's this whole range of narrow to broad tasks and knowing little and knowing a lot. And those, I think, demand different types of solutions. So let's think first about the structure of a policy. So how can we organize a good policy for a given distribution over possible domains? And I think the way we all operate is in some way to pick a model class and a way of acquiring the models for that class that perform well and that are relatively easy to construct. So if we think about construction cost, there's two kinds of costs. One is cost, human engineering cost, right? We might have to write down the model. We might have to build a simulator for training. We might have to work on reward shaping or gathering data. And there's also cost for machines doing various kinds of optimization, learning, and parameter tuning. And so when we think about what a good model class, what a good policy class is, we might want to find classes where humans have insight because they can help with the design, where it's easy to do optimization, and where learning will generalize best so that we don't have too much sample complexity. And certainly here, points 1 and 3 argue for structuring our approaches to learning. And I think 2 does also in a variety of ways, that it might be that if we could make smaller learning problems, those are easier to optimize than one enormous one. So let's think about how we can represent policies. Well, the most straightforward representation for a policy is not necessarily very structured. A representation for a policy could be a policy. And so that's a piece of software that takes in observations and maps them into actions, and it can be recurrent internally, let's say, so that it can remember the history of observations and actions. This strategy for representing policies isn't necessarily the best one. For humans, that means just straight up writing a program for the robot, or if we're going to use machine learning to acquire this, then we've found, I think, that search and policy space is good for short horizon policies that are actually difficult to engineer. but it's hard to extend to long horizon and very highly variable situations. So we might make a more structured policy. A more structured representation of a policy could be in terms of Q values. So this is very common. And we've already found that there are learning algorithms in many situations. It's easier to learn the Q values than it is to learn the policy. But once we know the Q values, then it's very easy to convert them into a policy. So this is one step toward structure in robot learning. One thing about learning Q values is that it depends on dynamic programming. Fundamentally, the idea is that we're going to many times reach the same state or very similar states, and that fact that we can reuse the solutions to subproblems gives us a lot of leverage. On some problems, that's definitely true. In other domains, we don't necessarily expect ever to visit a lot of the search space, and so it might be, or a lot of the state space, and so this might not be an effective strategy. As the domain becomes more and more complex, and in particular, the variability in the objective function, which I've written here as R, but it could be a goal, and the variability in the initial states is substantial, then rather than trying to compute a whole policy or a whole value function in advance, we might prefer to do some form of model predictive control, where we use a planner. Now we build in, let's say, a planning algorithm. So we're building in more structure. Maybe we build in something that says, I'm going to make a plan, take the first step in the plan, execute that in the world. Now we have to learn something different if we're going to be doing learning, a transition model or a word model, possibly, optionally, a policy or a Q function that can be used to guide the planning, but not necessarily. So these models, which I've written in yellow here, these are models we could learn or potentially that engineers could supply, but we've committed now to some algorithmic structure in the policy. So this is a good way to solve problems when the action space is kind of abstract, when we're not making controlled decisions very quickly, for instance, and the action space is maybe not too complex. But what we find is that in a lot of robotics problems, if the actions are low level, then the horizon is very long and the models are quite difficult to learn, the planning problems are hard, and so on. And so we might add even more structure. We might want to say that, yes, the long horizon planning is useful, but it's best if it takes place at a level of abstraction, maybe up above motor torques. So we might raise, in some sense, the level of discourse. We might say, architecturally now, that the way we're going to think about the problem is that we get raw observations in, but we use some models, some perceptual models, to aggregate them over time and to interpret images so that we get an S hat, a representation of the state that's more abstract. We might then have planning models now that we use at a higher level of abstraction. We may still adopt the model predictive control strategy. So we make a plan, take the first element. But now, instead of that being a raw action that we execute in the world, we might think of that first step in the plan as actually the selection of a controller, maybe a very tight feedback closed loop controller that we would now execute in the world. So here we have more blue boxes, so we have more structure, and we also have more models. We have perceptual models and control loop models that let us do our planning at a higher level of abstraction. We might go one level more and say, well, this planning might still be too long horizon, too difficult to do, and we can try to address that by adding some notion of abstraction. So we could imagine planning at multiple different levels of abstraction. And so instead of just having the control level and a planning level above that, we might have multiple hierarchical planning levels. So this is an architecture for a fairly general purpose, fairly high-level robot that I think might be useful for us in our learning. So, okay, if we're going to plan using high-level models, we have to think about what constitutes a good model for robot manipulation planning anyway. And we've kind of already argued that a raw simulator is not such a good choice. Generally speaking, the commands or torques are little localized position controls. The horizon is very long. It's difficult to hand write a heuristic. And so then we need some exploration to learn a value function to use as a heuristic, but then learning the value function is usually harder than solving the planning problem in the first place. So this doesn't necessarily work for long horizons. We propose instead to use a more abstract model. We're interested in action spaces that are lifted in the sense that they're independent of the particular objects in the world. So that if I learn something about how to manipulate some objects, I can immediately apply that to new objects without any additional learning. And we're interested in a compositional action space, in a situation where we can compose our actions together in an infinite combination of new ways to solve new problems. We would like to use hierarchy to reduce the horizon of any given planning problem that we solve, and try to use structure actually in the action space to allow us to apply various kinds of domain-independent heuristics. In this case, then, we don't need an exploration strategy. So if we're going to make an abstraction, we have to think about what makes an abstraction useful. Generally speaking, it should make your computational problem easier. It should make your solution quality not too much worse. An abstraction almost always makes your solution quality worse, but it's a trade-off you're willing to make. You'd also like it to be not too hard to implement or maintain, and to solve most of the problems you care about. So an abstraction that comes from robotics is super useful, I think, which is this notion of multimodal motion planning. In its basic form, the idea is that we assume that the robot and the objects are kinematic chains in some kind of 3D workspace, and we have a state that's represented in terms of poses and shapes of the objects. And we have this notion of a mode. You can think of the mode as the dynamics, smooth dynamics, kind of continuous, nice, compact dynamics of a small set of state variables as a function of how the robot is moving. And implicit in the notion of a mode is that there may be many, many state variables, like the positions of lots of objects, but that at any given moment, only a relatively small subset of those state variables can be changed. So when the robot's moving in free space, all it can change is the state variables having to do with its own joints. When it's holding onto an object, it can change the state variables involving that object's pose. Maybe when it's holding one object and pushing another, it can change some more state variables. But still, generally speaking, it can't change too many at once. And we can think about the planning problem as moving between modes or mode families. A family of modes is a set of modes that change the same variables, but where the static variables are the same. So I'll show you this picture that Hauser gave an original formulation of this problem, which has really been very influential. Recently, there's a paper with a figure that I like by Kingston and collaborators, and it really illustrates this notion that you can move in a mode, let's say a submanifold of the big space, like the robot moving in free space. And then when you get into the intersection with another mode, like that you have an object in your fingers, now you can move in that mode instead. And so you can think of planning in some sense as being hierarchical, in the sense that you plan a sequence of mode families to move through. You pick the particular parameters of the mode families, and then you do motion planning. And so that's a multi-level planning problem. So this abstraction is really very useful. We recently built a multimodal motion planner in the context of a task and motion planner. It had 4 mode families. One is to move freely through space. One is to pick an object and move while holding it and put it down. One was to move while touching an object, so to push it. And another one was to operate a 1 degree of freedom kinematic mechanism. And we used this to solve a whole collection of problems from the Meta World paper, which introduced a set of robot planning problems or learning problems to illustrate meta learning. But what's interesting is that by defining just these few modes and having a reasonably general purpose planner, you can actually solve most of the problems. In the end, we solved a large collection of the problems. There's some that we have not yet solved. One involves frictional interactions of the robot kind of rubbing up against objects, and so that's the thing that we hadn't put in yet. Another one involves pushing something into a hole that's very tight. So that notion of an abstraction is very useful. Now the question is, what role does it play in learning? So if you think about the situation on the bottom part of these axes, which is the one where the human engineers know the problem very well, there's a range of approaches we can take. There's classical engineering. So I have a spectrum here of blue to yellow. Blue involves really no learning, and yellow involves some amount of learning or a lot. Green is in between. So classical engineering says, we know something about we know a lot about what the robot's supposed to do, and it's not too complicated. We're just going to write the program. RL and simulation is an interesting setting where we say, we're going to do reinforcement learning inside a simulator that we build. So that's reinforcement learning, but it's still focused on offline solving a problem that we're then going to put the policy into the robot and execute. My research has been focused on this more notion of hierarchical planning and reacting to uncertainty in the world. And so far, it's been done pretty much completely using hand-built models. And so what we're really interested in is asking the question of, can we adopt a very general, very structured architecture like that, but push upward so that the robot can learn online as it encounters new things? So we might say, well, if the robot doesn't know too much, if the engineer doesn't know too much about what the robot's going to do, we could just put the robot out in the world and ask it to do reinforcement learning. The joke is, though, you really don't want the robot doing reinforcement learning in your kitchen when you ask it for a cup of tea. When you're online, you really, every single thing, every single piece of training could potentially break something in the world and cause negative reward, actual negative reward. And so you have to be very careful about sample complexity and about doing damage. So what we're going to think about is over here on the right-hand side, a way to take the hierarchical planning in the now HPN architecture, but think about an online interaction where the robot can learn new models incrementally while interacting with the world. So if we take this architecture, we might learn new controllers. There's already lots of work really in robot learning, most of it maybe on learning simple controllers that are useful and that might be composed in some way. We could learn perceptual models, so that's object recognition or understanding various kinds of place recognition. We could learn models, partial policies for the execution module, and we could learn models of the low-level controllers that the planner can compose. So I'm going to quickly just illustrate some of these ideas in work that we're doing right now, and then talk about how we might close the loop. So the thing that we've done that's kind of the most mature in some sense is work on learning operator models for new controllers. So the idea of modes, right, that there's a reasonably simple dynamics that controls some small set of state variables, that fundamental idea has actually been in robot learning since strips and shaky. So the foundations of actually classical planning and AI also have this idea that when the robot takes an action, it doesn't change too many state variables. So we can extend this idea. We can say, okay, imagine that we have a primitive procedure that we've learned. So one of those low-level controllers, maybe one that does pouring. We'd like to learn a description of the constraints of that mode. That is to say, what state variables have to be in what relationship so that if we execute that controller, it'll have a desired result. And I can write this down in kind of AI planning language. I can say, well, my desired result is that this destination container has some liquid in it. My skill is going to be the skill I've already learned. Maybe it's to pour. Maybe that skill has a parameter in it, like a gain. And at this point, I'm designing this by hand, although we could talk later about how to actually learn this. But you might say, okay, I believe that whether or not this pouring operation is going to be successful depends on some set of state variables in the world. It depends in particular on how I'm grasping the cup I'm pouring from, the shape of the thing I'm pouring into, the relative pose of the two things, and so on. And so those are a bunch of continuous state variables. There's the gain in the pouring skill, the grasp, the width and height of the vessels that I'm pouring to and from, the relative pose. And there's some constraint among all of these continuous variables such that if it holds and I call my pouring procedure, then the liquid will get into the desired container. And so what we're interested in doing is learning from experience that constraint. We formulate this as a Gaussian process regression problem. So we try pouring in lots of different situations. And we try to learn a mapping from those continuous variables that describe the situation of pouring into a score of how well it worked. What's important in that learning is that we end up with an understanding of the parts of the space where we're reasonably sure it will work and other parts of the space where we're uncertain. But also we're interested in being able to characterize the whole, as much as we can, the whole locus of successful pouring operations. So that, for instance, if in a planning context, a particular way of pouring is blocked, then we can find a different way to do it. We did this on the real robot, and we had to do a lot of training. In this case, we were learning pouring and scooping, and it was a lot of work picking up all those chickpeas and putting them back in the bowl again. So we're really interested in minimizing sample complexity, which we also do with the Gaussian process. But what's important is after learning those operator models for scooping and pouring and pushing and so on, we can integrate them with existing methods that the robot already knows. So in this set of demos, there was a lot of variability in the starting arrangement of the objects and the goal. We already knew how to pick and place objects. We have, in this case, a learned pour and push, and we're using a domain independent planner that Kaelin Garrett, one of our students, built. What's important is that the robot didn't have to relearn its own kinematics. It didn't have to relearn how to do pick and place. It was able to compose the new things that it learned with what it already knew to solve a whole new class of problems. One example that's nice, that's coming up in a minute, is that we asked it to pour into that red bowl. It learned about pushing and it learned about pouring, and it was able to immediately figure out by reasoning that it could push the bowl in front of it and then pour into it. So structure gave us an enormous amount of leverage in the learning here. We've been working on some neural network related methods for trying to learn models that apply across well, actually to learn which variables are important in predicting the results of an action. Another thing that we've been working on learning now a little bit is partial policies. So if you execute the same action sequence over and over again, it's good to be able to cache it. And we're using some techniques from inductive logic programming for thinking about that. We've been working on learning search control knowledge. So how is it that we can make the planner more efficient? And in particular, we've been focused on, again, on generalization. So imagine the robot learns how to, in this apartment over here in the bottom right, to, let's say, move that red box into the kitchen by moving the other boxes out of the way. Can it take what it learned and apply it now in moving smaller objects in a cupboard? And we do that by doing a kind of Q learning, but at a higher level of abstraction that we think generalizes across problems more effectively. So in the end, what we hope to have is a kind of a compositional, continual, cooperative learning architecture. The cooperative part means that we're also going to be interacting with a human who can supply some advice and some hints. Imagine that you bought a robot from us and you want to teach it a new skill, like it doesn't know how to beat eggs or maybe how to solder. So the question is, how could you take a robot that already knows a fair amount about how to do things and teach it a new skill? So the robot also in its free time could pick a target property that it would like to learn about, try to plan given what it knows to make that property true. If it can find a plan, execute it and see what happens. If it can't find a plan, try to figure out why not. Maybe it needs a new primitive skill. And if it needs a new primitive skill, then it should be able to formulate a little localized reinforcement learning problem to learn that new skill. Or if it can't find a plan step, maybe we have to learn a model of a skill we already have that extends more broadly. Once it's executed a plan, then it gets data and it can use that to update its predictive models. It might be able to compress its models by defining new concepts. That's something that we've done some work exploring in another context. If it defines a new concept, like maybe something is contained in something else, then it can potentially learn how to make that true. It can take new latent properties. Maybe there's hidden properties, like these objects stick together when I don't expect them to. Maybe they have magnets embedded in them. So maybe I could invent a new property and learn to predict that and learn to make it true or false. And then this loop can go on and a robot could learn more and more as it goes. So we hope to be able to do learning of a broad variety of things by taking advantage of a structured architecture and maybe with some hints and advice from humans along the way. So I want to thank my colleague Tomas Lozano Perez and students who worked on these projects and also other students in my group. And if we were here live, I would let you watch robot outtakes where it did some near misses of a variety of entertaining kinds. Unfortunately, we're not all in the same place, but I understand there's a panel discussion and maybe there will be an opportunity to ask some questions then. Thanks.